Specific comparisons correlated. In the weapons and aggression case study, subjects were asked to read words presented on a computer screen as quickly as they could. Some of the words were aggressive words such as injure or shatter. Others were control words such as relocate or consider. These two types of words were preceded by words that were either the names of weapons such as gunshot, shotgun, and generate, or non-weapon words such as rabbit or fish. For each subject, the mean reading time across words was computed for these four conditions. The four conditions are described in this table. AW is the time to name an aggressive word following a weapon word prime. AN is the time to name an aggressive word following a non-weapon word prime. CW is the time to name a control word following a weapon word prime. And CN is the time to name a control word following a non-weapon word prime. This table shows the data for 5 of the 32 subjects in this experiment. All times are in milliseconds. Subject number 1 took 447 milliseconds to read an aggressive word that was preceded by a weapon word time, the AW condition. One question this experiment was designed to answer was whether reading times would be shorter when the preceding word was a weapon word, AW and CW conditions, than when it was a non-weapon word, AN and CN conditions. In other words, is the column L1, which is equal to the quantity of AN plus CN minus the quantity of AW plus CW greater than 0? This is tested for significance by computing L1 for each subject and then testing whether the mean value of L1 is significantly different from 0. This table shows L1 for the first 5 subjects. L1 for subject 1 was computed by taking the sum of 440 and 452 and subtracting the sum of 447 and 432 from that value. This equals 13. Once L1 is computed for each subject, the significance test is the same as testing whether a single mean is significantly different from 0. First, we compute the mean and the standard error of the mean for L1. Computing L1 for the 32 subjects in the experiment, we find that the mean and the standard error of the mean are 5.875 and 4.265, respectively. T equals 1.378. Since there were 32 subjects, the degrees of freedom is 32 minus 1 equals 31. The t-distribution calculator shows that the two-tailed probability is 0.178. Thus, we are unable to reject the null hypothesis, and we cannot make a confident conclusion that reading times are faster when there is a weapon word prime. A more interesting question is whether the priming effect, or the difference in reading times between words preceded by a non-weapon word and words preceded by a weapon word, is different for aggressive words than it is for non-aggressive words. That is, do weapon words prime aggressive words more than they prime non-aggressive words? The priming of aggressive word is the quantity of AN minus AW. The priming of non-negative word is CN minus CW. The comparison is the difference. L2 equals the quantity of AN minus AW minus the quantity of CN minus CW. If weapon words do not indeed prime aggressive words more than they prime non-aggressive words, then we would expect the difference between AN and AW to be larger than the difference between CN and CW, so L2 would be greater than 0. This table shows L2 for the first 5 of the 32 subjects. The mean and standard error of the mean based on all 32 subjects are 8.438 and 3.913 respectively. Therefore, t equals 2.156 and p equals 0.039. Our p-value is below 0.05, so we can reject the null hypothesis. L2 is significantly greater than 0, so we can conclude that weapon words prime aggressive words more than they prime non-aggressive words. Issues associated with doing multiple comparisons are the same for related observations as they are for multiple comparisons among independent groups. This means that you may need to do a Bonferroni correction and control the family-wise error rate by lowering the per comparison error rate.